Find the minimum value of the function f of x. In this problem, we've been provided a function f of x, which is a function of variables x1 and x2, and represented as the curved surface, which is shown in aquamarine. The problem also provides the constraints. x1 plus x2 is at most 2, and the constraint negative x1 plus 2 times x2 is at most 2. If we view a contour plot which looks down upon the x1, x2 plane, then we notice the level sets of the objective function decrease as x1 and x2 increase, generally speaking. The first constraint confines the feasible region to values of x1 and x2, where x1 plus x2 is at most 2. The second constraint confines the feasible region to values where x2 is at most 1 plus 1/2 x1. The union of these two feasible regions is shown in green. If our minimizer is located along the upper right boundary of the feasible region, then the first constraint will be active. If the minimizer is located along the upper left boundary of the feasible region, then the second constraint will be active. To solve this problem, we'll write the objective function in its quadratic notation, 1/2 x transpose qx plus c transpose x. Solving for q and c, we get 2, -2, -2, 4 for q, and -2, -6 for c. If we define a constraint set, ax is at least b, then, looking at our constraints, our values for a and b become -1, -1, 1, -2 for a, and -2, -2 for b. Next, we'll introduce the Karush-Kuhn-Tucker conditions for optimality in a nonlinear optimization problem. Feasibility simply states the optimal feasible solution must be a feasible solution, where S represents a non-negative slack vector. For feasibility to hold, all vectors x, s, lambda, and pi must all be non-negative. And finally, we'll write out these feasibility equations. Complementary slackness is the next KKT condition, which means lambda transpose s equals 0 and pi transpose x equals 0, where s equals -ax plus b, the primary constraint set, and lambda equals the associated dual variables for these constraints. Vector pi represents the dual variables associated with the non-negativity constraints for all x variables, which are constrained in vector x. Next, we'll formulate an equation y equals mz plus q, which can be expanded to include our vectors pi, s, q, a, x, lambda, c, and b. To begin, we'll assume vector y is basic, which means the values are not constrained to equal 0 and must be non-negative to form a feasible solution. The values in vector z are non-basic and must equal 0. To find the solution, we'll use Lemke's algorithm, which replaces the most negative component of vector y with the appropriate component of vector z, until vector q is non-negative, and all variables in the basis are real. After substituting in each known value, we'll write out the four equations. Since all non-basic variables x1, x2, lambda 1, and lambda 2 equal 0, our basic vector y equals the vector q. That is, pi 1 equals -2, pi 2 equals -6, and so on. Since our objective is to make all basic variables non-negative, our strategy will be to add an artificial variable z0 to each of the basic variable equations. Then, in the first iteration, we'll replace the most negative basic variable in vector y, which is pi2, which has a value of -6, with the artificial variable z0, such that all basic variables are non-negative. Next, we'll solve for this second row for z0, and write out z0 in the second row of our next iteration. After that, we'll plug in this value of z0 for the other 3 rows and update our equations for the basic variables pi1, s1, and s2. At this point, all basic variables are non-negative. However, we need to remove the artificial variable z0 from the basis to have an optimal feasible solution. Since we are trying to drive z0 down to 0, we'll look at the variables with negative coefficients in this row, which are x2, lambda 1, and lambda 2. If one of these 3 variables increases in value, then z0 will decrease in value, which is our objective. However, since variables s1 and s2 are already basic, then from complementary slackness, variables lambda 1 and lambda 2 cannot become basic and must remain equal to 0. Therefore, we'll choose non-basic variable x2 to enter the basis. We'll use the ratio test to determine which of the 4 basic variables will leave the basis. In the ratio test, we'll divide the value of each basic variable by the coefficient of the variable entering the basis, and the row with the smallest quotient, which is negative, which turns out to be -4/6, will correspond to the row which will become non-basic, which in this case is the row for pi1. The ratio test is used to ensure variables in the basis remain non-negative. As before, we'll pivot about our chosen variable x2 in the row pi1, solve for x2, and write out x2 in the next iteration. Then, we'll plug this value into x2 for rows z0, s1, and s2. And lastly, we'll update those last 3 basic variables. After this pivot operation, we notice the values of all basic variables decreased. Most importantly, the value of variable z0 decreased from 6 to 10/3. Since z0 is still in the basis, we'll perform another iteration. The variables with negative coefficients in the row z0 are x1 and lambda 1. As before, complementary slackness prohibits lambda 1 from entering the basis, since variable s1 is 14/3. Variable x1 can enter the basis and become non-zero because variable pi1 is non-basic and already equals 0. Next, in the ratio test, we learn that basic variable s1 will leave the basis because it has the smallest ratio that is negative among all 4 ratios. Therefore, we'll solve for x1 in row s1 and then write out the equation for x1 in the next iteration. After substituting this value in for x1, we can update the equations for the basic variables x2, z0, and s2. We notice the value of z0 decreased from 10/3 to 2. In the next iteration, we'll choose lambda 1 to enter the basis. And from the ratio test, we learn variable z0 will exit the basis, Therefore, we'll perform one last pivot operation about variable lambda1 in row z0. And our final basic variables are x2, lambda1, x1, and s2. Since variable z0 is an artificial variable and non-basic, we can remove this term from the equation. Finally, we notice our minimizer is located at x1 equals 4/5, x2 equals 6/5. If we return to our contour plot, our minimizer, x star, plots on the top right boundary of the feasible region, which makes sense because our first constraint is active. When plugging in 4/5 and 6/5 into the objective function, our minimum value of f of x equals -7.2. When reviewing the possible solutions, the answer is D.